Hello. We solve some problems on same compensator design based on bode for this week.
Okay, ma'am.
Okay. So in, we'll start to solve these problems one by one. As I did on Wednesday, we are going to solve using MATLAB tool this time also.
Okay, ma'am.
In the first problem, first we'll have some idea about the problem. First, the first one to seventh one was under the same section. Okay. The first question asks, they have given a transfer function and they ask what is the value of k that will result in a velocity error constant. This we can calculate using hand also. The second question, with the k we have found from the question 1, we have to check whether the closed loop system is stable. This we can either go with a standard formula if it is a second order system. Otherwise, we can write a Routh-Hurwitz array for this and find whether the system is stable or not for the value we found in the question number 1. Third one is the gain crossover frequency they have asked. Gain crossover frequency occurs at phase margin, right? So first we need to plot the bode plot for the given transfer function with k mentioned. And then we have to look for the stability margins. In the phase margin, we will find the corresponding frequency. That is the answer for the third question. Fourth question is choose alpha of the lead compensator as given 0.14. With this choice of alpha, what is the maximum frequency? So Wednesday we solved some problem where to find the maximum frequency, we will solve the maximum angle, and then at that with that help of those we will find the maximum frequency. That can also be done here with this choice of omega m and alpha. What is the phase margin again? This is for the newly compensated system. Then gain margin they asked for the new system, bandwidth, and that's it for the first question. Okay. So we have all the ideas we have done so far, so many problems we have solved. So based on that idea, we can easily solve this, I guess. If you have any doubts, you can stop me then and there and we can do it. Okay. First, I will write the transfer function. T1 is equal to k into 10 divided by s into s by 6 s by 6 plus 1, right, into double bracket s by 2.5 plus 1. That's it. Okay. We'll first check whether the transfer function is right or not. Okay, k I'm taking equal to 1 for now to check. This is equal to f of s. I'm defining the transfer function variable s. Okay, 250 divided by s cube, some s constant won't be there because everything will be multiplied by s, right? Okay, good. Then the next question is, what is the value of k that will result in a velocity error constant of kv equal to 10? That we are going to find now. Okay, how to do that? Kv equal to, I'll just write it here for the first question. We know the formula kv equal to limit s tends to 0 s into g of s, right? Is equal to, it was given in the question. What is kv? Kv is 10 was given. So it will be 10 equal to limit s tends to 0 s into the whole transfer function here. This will come. Okay. So we'll just solve it by hand and let me know the k value. Put s is equal to 0 in all these things. So if I put s is equal to 0, 10 equal to k into 10 divided by whole, everything will be 0 right here. There are, oh, okay, this s and this s will get cancelled. This s and this s will get cancelled. Then the rest of the things are 1. This will be 1, 0 plus 1, again 0 plus 1 will be there. So it will be 10 is equal to k10. So the next problem, next line would be this 10 and 10 will get cancelled, k equal to 1. Any doubt in this? I
No,
have
ma'am.
done correct? Okay, right. So the first gain we have calculated, k as we fixed earlier, this is 1 for this problem. Okay, going ahead with the second question. What is the second question? With the choice of k as in question 1, is the closed loop system stable? I will tell you how to find the stability in MATLAB. Meanwhile, you can calculate that using your hand. So if I substitute 10 here in this problem, what it will be like the closed loop transfer function, can you say?
Substitute k is 1 only, no, ma'am.
K is 1. So the transfer function will be 10 by.
Uh, so yeah, the characteristic equation would be 10 plus the denominator.
Uh, so if we simplify this, can you give me in terms of quadratic equation or cubic equation? It is third order. No? Do all this s by 6, s by 2, 5, 2.5. So this will be 10 divided by s into s by 6 plus 1, s by 2.5 plus 1. So, because k equal to 1. That's why. 10 divided by s into, this will be 6s plus 6. 6s plus 6 by 2.5. Again 6.5 into 2.5 into 6 into 2.5, yes, plus 6 into 2.5 into 6, yes, plus 6 into 2.5. All this, okay, again, why do we need to complicate this much? I can do this like this, right? S plus 6 by 6. Yes, plus 2.5 by 2.5. 10 by S into S plus 6 into 2.5 into 6 into 2.5. Right? This will give me 16 to 2.5. 50 divided by S into S plus 6 into S plus 2.5. This is your open loop transfer function. If you want to find the stability, you have to find the closed loop transfer function. Is it given anything like that? Unity feedback? Nothing. It was not given anything, but just we will assume unity feedback since it was not given anything over that. So this will be g of s plus 1 plus g of s h of s. That will be 150 divided by s into s plus 6, s plus 2.5 plus 150. So overall transfer function is s squared plus 8.5 s plus 15 plus 150. 150 divided by s cube plus 8.5 s squared plus 15s plus 150. If you have some other characteristic equation, if you are getting, let me know.
Same, ma'am. But I'm
Same.
not seeing your screen, ma'am. But what you said is right.
Okay. Oh, I've been presenting from my iPad. It's not visible.
The MATLAB screen is there.
Oh, that is the only there. Okay, wait. Is it visible now? No?
Yes, ma'am.
Okay, right. Now, what I did is I just calculated this, multiplied this 6 with here, 2.5 here. This I'm telling for people who are listening like offline videos. So I have multiplied the 6 here, 2.5 here, and took the 6 and 2.5 above here. So the overall open loop transfer function will look like this. If I calculate the closed loop transfer function, this 150 will come here plus, since I'm assuming unity negative feedback. So this is your overall closed loop transfer function. So stability depends on the poles. Usually we calculate for closed loop transfer function. That's why. Now I am going to calculate the route array for this. First we will write odd arrays first, then even arrays. So I'm starting with x cube. So 1, and the next odd is this 15. There is no another odd, so it will be 0 here. You don't need to write that also. The next s square coefficient is 8.5. This one, and another one is s power 0, that coefficient I'm writing here. How do we do Raut-Horowitz array? First,
8.3 to 15 minus.
yes, yeah, right. First we will multiply this and we will multiply this, and both of it will be subtracted and divided by this 8.5. So it will be 8.5 into 15 minus 150 into 1 divided by 8.5. So how much this will give? Can you calculate and tell me? Or I will use calculator. 8.5 into 15
minus 2.65 roughly.
minus 2.65. Minus 2.65. From this only, we will know that it is unstable. We don't need to calculate all these steps because the question asked about closed loop system stability. Here, one sign change happens. Both are positive, but from positive minus happened. So the system is surely unstable. Still, we will calculate the rest of the things also. So this is again, this will be this into minus this divided by 1. Since this is 0, or whatever coefficient here will come here. Again, one sign change happened from minus to positive. In general, the system is unstable just because one sign change happened, but the sign changes from positive to negative one time, negative to positive one time. Two times the sign change. So two poles are in the right half of the S plane. This is another question. If someone asks how many poles are in the right half of the S plane, by giving a characteristic equation or an open loop system, you should be able to find the closed loop transfer function, then do Routh-Hurwitz, see how many times the sign changes, then come to the conclusion that number of sign change, number of times the sign changes equal to the number of volts in the right half of the S plane. Right. Now we know the system is unstable, closed loop system is unstable. Okay, I will present again from my laptop. Okay, right. Now we will see what is the next question. Next question asked, what is the gain crossover frequency? For this, we have to plot bode. So we are plotting bode for the third question. Gain crossover frequency they have asked. For this, I am going to plot bode for the transfer function. Okay, we got the bode for this system, and I am calculating characteristics, all stability margins. It gave the phase margin and gain margin. Gain margin is at minus 1.41 decibels. Phase margin is minus 4.17 at frequency 4.2. So your gain crossover frequency happens at phase margin value. So your phase margin is minus 4.17 at frequency 4.2. So your gain margin, sorry, gain crossover frequency is 4.2. Omega, I'm just writing W minus underscore gain crossover frequency is 4.2. Sure answer. Right. What is the next question? Choose alpha of the lead compensator. Alpha is as given. And with the choice of alpha, what is the maximum angle? Omega m we are going to find. Right. For this, what formula? We have been familiar with the formula, right? First, how this can be connected?
Which one, ma'am?
Formula to find the omega m. Omega m equal to 1 by t into root alpha. You know that?
Oh, yes, ma'am. Yes, ma'am.
Yeah, we can use that formula here, but we have to find the t for that, right?
Oh, yes,
Time
ma'am.
constant we have to find.
Alpha also we have to find.
Alpha is given in the question.
Okay. So T we will find from omega m now, ma'am.
Yeah.
So how do
Otherwise,
we find omega m?
no, we can find directly from this uh,
Plot.
it- I will type it here. Minus 20 log of 1 by root of.
Oh, okay, okay.
Okay, if you find the margin of this, there is a uh,
I mean, can't we find it from the graph directly, ma'am?
we can do. Otherwise, we can, if you want it specifically, this is another
Oh,
command
okay.
you can use to get that.
Yes, ma'am.
Okay, sorry, not G. TF1 we have defined. Margin, it is given in the, see, here gain margin and if phase margin will be mentioned here. If you put margin along with the bode, you will get gain margin and phase margin instead of doing all this stability margin here. Other than that, if you want to directly get that from here, you have to assign this. It is a kind of array that you can assign gain margin, phase margin. This is the mm, like correct order to mention. Gain margin, phase margin, gain crossover frequency, phase crossover frequency. Okay, equal to whatever margin you found now. Margin of TF1. Then this will give you everything like in mm, gain margin is 0.85, phase margin is minus 4.165, phase gain crossover frequency is 3.87, phase crossover frequency is 4.1952. That this will give. Now, if you want to find the magnitude, sorry, for the fourth question, what it's been asked, alpha is given. We have to find the maximum frequency or frequency at which the maximum phase lead occurs. Actually, we can get it from the diagram. Maximum phase lead occurs here around this point. But exactly if you want to find, you can look for the same magnitude here and calculate from that using the alpha. The formula to find that is minus 20 log of 1 by root alpha, SQRT I'm writing, root alpha. In MATLAB, you will write it in terms of SQRT for finding the square root. That will be equal to the magnitude you will be finding.
Minus is there or not? In
It will be there. It will be there.
on the lecture, it was not there.
In the lecture, it was not there. Okay, 1 minute. I'm trying to find it from the image itself. I don't remember that exactly the formula. Bode of TF1, if I try omega minimum, this will give me minimum and maximum of omega. Okay, I can't remember it. Magnitude, if I take phase, is equal to bode of TF1, comma, omega I have to define, right? That I'm defining as log space, some minus 1, comma, 2 comma 2000 if I want to say. Okay, magnitude and phase I'm getting all will be there. If I skew, I will check if it is correct and then explain what I'm doing. Skew
Okay.
magnitude. Okay, I'm getting magnitude. If I find the index, find it absolute of, I want to try using 20 log of magnitude, right? Minus of there, minus of minus 8.4315. Stick. It's also log 10 should be right. It's in the zero. Okay. Then I will do instead of this, I will take W. Okay. Then it will index. Oh, it's not. Different rate compensator with also alpha. What is the maximum frequency? It is to phase read upwards. We'll calculate by hand, then this is a little calculating from here, it's a little bit tedious. So we'll go with general formula. So this will be equal to your magnitude of your transfer function, right? So if you put minus here, you have to put minus here. Anyway, we don't have to use form magnet like minus here. So we will try to find the magnitude of the transfer function. That will be your absolute value of your TF1, whatever transfer function. You can calculate that by hand. It will be 10 by this value. If you find it, you will have, oh sorry, that's for closed loop like loop transfer function. 150 divided by s into s plus 6 plus s plus 2.5. That's what we have calculated here, right? 150 divided by s into s plus 6 plus s plus 2.5, that you have to calculate. It will give me 50 divided by 150 divided by 6 into 2.5. This will be
Ma'am, that screen shift.
screen. Okay, this is just calculation. We are going to use only MATLAB.
Okay.
Um, 25 by 2.5, it will give me something around, it will be equal to 20 log of 1 by root of sqrt of alpha. It is 1.0.14, they have given. It will be equal to 8.53 around, I am getting. So from this, you have to find this value 1 by 20 log. So I will take 20 here, log 1 by sqrt of alpha 0.14 is equal to 8.53 by 20. 8.53 divided by 20, how much I'm getting? 0.425. Right? Now I have to find 10 power 0.425 is to get rid of alpha 1 by sqrt of 0.14 is equal to 2.67. Then this will be sqrt of 0.14 is equal to 1 by 2.67, 1 divided by 2.67, taking inverse 0.3745. Then what am I calculating? Actually, alpha we have already, right? Okay, we don't need to calculate because there is nothing in the formula, all are constants, right? Just we have to find
That's
this magnitude
8.53.
here.
Yes, ma'am. Actually, the
The
magnitude,
frequency
yeah,
at which,
yeah, omega m we have to find, ma'am.
yeah, the frequency at which magnitude. I thought the omega m is there in the uh, formula. So the frequency at which this 8.538, where it is magnitude, it's lesser here now. Okay, delete on somewhere around here, 4.6 point, 8 point
53.
something between this 2.5 something. So not very accurate, but around 2.5 we will be getting for that. Okay, with this choice of omega and alpha, what is the phase margin of the compensated system? Now we are going to use the same omega m, what we found there, and alpha we found. Actually, this is a lead compensator, right? So lead compensator will look something like this. Lead compensator.
50. We have to find T.
1 plus st divided by 1 plus alpha is t. That's how your lead compensator would look like, where alpha will be in between 0 to 1. Where our alpha, it was given as 0.14. Now we have to find the omega m, we have to find the t. Omega m we know that is around 2.5 we found. So the formula will be omega m, or I will just say omega wm, that is in short for omega m, equal to 1 by sq or t root of alpha. Only root will come for alpha or both alpha and t? Only alpha, right?
Yes, ma'am. Only alpha.
Only alpha it will come. Okay. Then the t can be found using 1 divided by omega m into sq or t of alpha. All the values we know here. So the t will be equal to 1 divided by omega m is 2.5 around we found into sq or t of 0.14. Just checking alpha values correct. 0.14. So sqrt of 0.14 into 2.5, 0.9354, 1 divided by answer 1.06. That is your t. 1.06 your time constant. Alpha, you know, now 1 point alpha 0.14, that we know. Now we know that compensator. So your overall compensator will look like TF of compensator is equal to 1 plus S into 1.06 divided by 1 plus S into 0.14 into 1.06. 0.14 it is. 0.1484. This is your compensator transfer function. Lead compensator. Just lead. Okay. Lead compensator transfer function we have designed. Then what they are asking? Phase margin. So now just we have to write this transfer function as T compensator, right? And we know
And
the overall.
one plus
Did I make any mistake?
typo.
Where?
First, yeah, there.
Oh, there it is. Oh, thank you. Please make sure I'm not doing any of this thing right. Okay. T compensator. Right. This is my overall transfer function. Now I have to do another bode for this T of overall. Okay. Sorry. Figure bode of T of overall. Okay. This is the old bode for the uncompensated system, while figure 2 is the bode plot for the compensated system. You can see the difference between these two. If I, this gain margin, phase margin, it was mentioned here. Now I am going to put it for this. So this gain is infinity for the system. Phase margin is 32.7. So that is the new phase margin for the system. Oh, gain margin only the phase margin is 32.7 around. Gain margin is infinity. If for 3 decibels you cannot find, I guess. Since the gain margin is 0, we'll check. It's there. Minus 3 decibels. Around 14, 15.2. No, it's very, okay, around 15. I'm going to take. That's the bandwidth. Okay, 15.4, around 15 is your bandwidth. That's it. We have solved question 1. So type infinity whenever the answer is here. That's it. Okay, we are going to solve the next set of question. This set of question 8 to 15 represent the same question. First question, they have given a transfer function, that is open loop transfer function. It is desired that the compensator system has a velocity error constant kb equal to 10 and phase margin equal to 40 degrees. Now they have given the criteria. They want the velocity error constant to be 10 and phase margin to be 40. There is no k given in the question, so no need to find any k. We'll just assume k equal to 1 now. Excuse me.
Yes, sir.
Sorry. Okay. So the design criteria they have given, the velocity error constant is 10, phase margin is 40. What is the phase margin of the okay? This is for the compensated system. The question is little inverse out of it. What is the phase margin of the uncompensated system? They are asking. That can be found from the transfer function itself. And what is the value of compensator gain needed to achieve the required steady state error? Okay. And it is a closed loop system stable with choice of k. Okay, this k here will come not come from the open loop transfer function but from the compensator controller. Compensator that is going to be act as a controller here, where we will consider k by s or k by s plus a kind of compensator we want to design. If we design a lag compensator, it is k into s plus a divided by s plus b, then the numerator will be lesser, the poles will be farther than the zero, but sorry, left than the zero, or if we design a lead, it will be right than the zero. So that's how it is. So based on that design, this k in question 10 belongs to the compensator k. And question 11 asks what is the PM of phase margin of the gain adjusted system. 12 is okay, beta has been given here. So there is a clue in this question that we are required to design a lag compensator for this. Okay. Then from that it is asking T they have given. What is another phase margin of the again lag compensated system? Maximum phase lag 5 m they have asked and gain margin test. Okay. Then we will solve one by one. The first question is they have given a system, an uncompensated system's phase margin they are asking. It's a simple system 1 by s into s plus 1, second order system. TF1 is equal to 1 by s into s plus 1. Before that, we have to tell what is s. S is equal to transfer function of this. Okay. No. Bode of transfer function 1. And we can say margin of yes. Then the margins will be given there. Okay. So gain margin is infinity, phase margin is 51.8. If you do the same for the stability margin, if you found that also you will get the same answer here. Phase margin is 51.8. That is the phase margin of the uncompensated system. For question 8, phase margin of uncompensated system we found. How much we found? It's 51, right? 51.8. In the first question, phase margin of uncompensated system is around 52. I'm taking roughly. Question 2 is what is the question 2? What is the value of the compensator gain needed to achieve the requirements on the steady state? So kV equal to 10. That's what they are referring to. That is the steady state value. What is the compensator gain you need to do? Just you assume that you have a K in the open loop system, and then we will find the value. KV, same formula. KV equal to limit S tends to 0, S into G of S, where G of S here is KV we know 10 equal to limit S into S tends to 0, S into K by S into S plus 1. Right? So if I put S, this S and this S will get cancelled. It will be K by S plus 1. If I put 0 for that, 10 equal to K by 1. It will be. So K equal to 10. Now the transfer function that satisfies this steady state condition is 10 by S into S plus 1. Right? Satisfies the steady state condition. So for question 2, it's done. Question 3. Next, we are going to see the transient conditions that satisfies this phase margin. We are going to design compensator that satisfies this phase margin of 40 degrees. For now, the uncompensated system's phase margin is 52. We are trying to bring it down to 40. Minimum is here. No, it's equal to phase margin of 40 degrees we want to design. Then the next question is the closed loop system stable with this choice of K? From MATLAB, how can we find it? Last time I told, but I didn't mention how we can find poles of this transfer function. That will give you what are all the poles, uh, what are all the poles of the transfer function. But here, this is the open loop transfer function, right? First, we need to find the closed loop transfer function to find the stability. How we can find that is the formula for closed loop transfer function with unity negative feedback. This works for unity negative feedback is TF, comma 1. 1 represents the unity negative feedback. This feedback is for negative feedback. 1 is for unity. If you have some other feedback in your feedback loop, H of S is equal to 3 or something, that you need to put here. So this is for unity negative feedback. Now if I calculate, I have mentioned as my system is TF1, right? So closed loop TF1 is equal to feedback of TF1 comma 1. Then poles of closed loop TF1. Oh, sorry, not poles, it's pole. Okay. So this is your closed loop transfer function. It's 1 by S square plus S plus 1. That's your closed loop transfer function. And your poles are at minus 0.5 plus 0.8 J and minus 0.5 minus 0.8 J. So my poles are at minus 0.5 plus or minus 0.867 J. So this is a stable. So my closed loop system is stable, right? I hope there is any doubt.
No.
Is down. Then fourth is, what is the phase margin of the gain adjusted system? So gain adjusted system is this one, whatever we found for the question number 9. We adjusted for the steady state value, right? Now we have to find bode figure, phase margin of gain adjusted system. Figure bode of, I will write transfer function 2 equal to, where it is 10 by s into s plus 1, right? Okay. Here already bode of ts2. Phase margin has reduced further to 18. From 52, it has become 18. So now we have to increase the phase margin from 80 to 40, right? So 40 is the desired phase margin. It was 51 before, 52 before, now it has become 18. Right? Phase margin of gain adjusted system is 18. With we are required to design a lag compensator given in terms we know what is the value of beta allowing additional 10 degrees to account for the additional lag introduced by the compensator. So already we have 8 for 40 is our criteria. Additional lag of 10 we have to consider, that is 50. So for designing the lag compensator, first we have to write the lag compensator representation. How we used to represent, that is 1 plus st divided by same 1 plus s beta s into beta t, where beta will be, in order to have a phase, okay, we our now the phase margin criteria will be 50 because additional phase lag we have to consider. So now if you want to find the deficit of the phase margin, the phase margin is equal to minus 180 plus whatever phase margin we need, or gain crossover frequency we will need. So this will be it's correct, right? Phase crossover frequency. Okay. Now it is phase margin we need 50 is equal to minus 180 plus PGC. Now PGC will be minus 130. We have to look at minus 130 in the bode plot of the gain adjusted system. So where this minus 130 occurs? Occurs at frequency 0.85. Okay. The minus 130 occurs at frequency 0.85. So we have to shift the system from this value 18 degree phase margin to 40 degree phase margin, so that it will come here, the phase margin will come here. This compensation along with this 10% compensation will happen at 0.85. So the corresponding frequency is 0.85 here. Right now the omega for the compensation is 0.85 around radians per second, I want to say. So we have to find the gain at which this frequency occurs, right? For the compensated system, just above this, the gain at which this frequency 0.85, we will look for the same frequency the gain corresponding to the same frequency. It's around 19. Magnitude is 19. So this is the gain. I think it's a separate question. No, same question only. What is the value of beta we want to find, right? We know the gain now. We know the phase at which this happened. Then we know the formula 20 log of 1 by beta is equal to this magnitude. So it's equal to this magnitude. The magnitude, how much I found? It's 19, right? Actually, negative point is negative, minus is there. Minus is there for lag compensator. It is correct. With minus only calculate. So this will give me 19.2 divided by 20, you will get 0.96 log of 1 by beta is equal to 0 minus 0.96. 1 by beta is equal to 10 power minus 0.6. 0.1096 beta equal to 1 divided by answer 9.12 around 9.1. Yeah, it's correct. It should be greater than 1 always, right? Whatever value, there is no upper bound for this. So beta is 9.12. It's the answer. We have calculated the beta. Choose t equal to 10 and what is the phase margin of the compensator system. Now just substitute in this transfer function, lag compensator transfer function. It is 1 by st equal to 10, beta equal to 9.12, 9.12 into 10 again. So this is my compensator transfer function, lag compensator transfer function. 1 by s plus s into 10 divided by 1 plus s into 9.12 into 10. This is my transfer function. TF overall will give me TF compensated into my gain compensated system, not the first one. TF2 I'm taking. Okay. So this is the compensated transfer function, compensator transfer function. This is the compensated transfer function along with the original system. Now we are finding the bode for this to check whether it has adjusted. Okay, right. The phase margin comes around 43.2. It's not perfect as 40, but it is okay. Around 43. We just have to change a little bit here and there to get the 43. But this is allowable, not it's not a bad one. We design a good compensator. From 18 degree, we have pushed to 43-degree phase margin. That's the around 40 degree what was asked in the question. What is the frequency at which the maximum phase lag occur in the compensated system? So this can be found using the figure itself. It's occurring here around point 3, 0.03 around will be. That is 0.03. And what is the gain margin?
How
Gain
much?
margin is
Like,
all.
how do we find the maximum phase loss?
It can be found using the formula of omega m there also, but in the figure, you can find it using the dip where it is like coming happening.
Oh, okay.
Here is the dip, so it's around 0.03. But if you find using the formula, you will find this phase first. So after finding the phase angle, you can check the frequency at this phase angle. That also will work.
Okay.
Okay. And the gain margin is infinity. Overall, for all the systems, we found only infinite gain margin, right? So for the last question, gain margin is the infinity. So that's what I wanted to discuss for now in this session. So if you have any question regarding your assignments, you can ask. And regarding the assignments, I want to make an announcement. We have opened a week 8 submission again. Some of you only submitted through the G form link. Rest of you have submitted the answers in the peer review. Around 40-45 of you have submitted in the peer review. But peer review is for different purpose. Submission of assignment should be done using the G form. So try to submit again. Since you have 2 days, if you even if you haven't written your assignment, you have this time. So take this time and solve your assignment for week 8. Submit it along with the MATLAB code to the G form. Okay, it should be like whatever you solved as a PDF. Then again, the MATLAB code should be attached as .m file. Everything should be put together inside a zip file. Then upload it in the G form. So your evaluation for week 8 will be done like this, and week 9 same procedure. Write your
Okay.
answers in the PDF, attach MATLAB codes, put everything inside a zip and upload it in the G form. Okay.
Okay.
Right. I will post this in the discussion forum, whatever G chat also, to remind students.
Okay.
And we can solve few other problems if we still have time, right? So we'll solve some like one mark, 2 mark question because your NSEM is computer based questions, right? I will look
Oh,
for
so
some
in some
questions.
there won't be any paper-based questions, is it?
Nothing. Everything is computer based, like you did for quiz.
Okay. Oh, why, ma'am? Like, lot of students? Mm.
Yeah, last time we had this written based, but it was not good. Like the
Okay.
outcome was not good, so we
Oh,
decided to go with 1 or 2 marks.
okay.
My iPad is visible, right?
Yes, ma'am.
Right. Okay. Oh, I will take another transfer function like this. S by 3 plus 1 into s plus 1 into 3s plus 1. During this, our requirement is to design a lag compensator. So far we have done on everything using velocity error constant. Now we choose position error constant that should Kp should be equal to 10 and phase margin is at least 25 degrees. Keeping this in mind, the first question is what is the value of K that meets this steady state? Just this is for your practice we have done so far. So you know the KP formula, right? The You should find the K value in GS such that it meets KP equal to 10. So your KP equal to limit S tends to 0, K into G of S, K into G of S, how does by plus 1 is plus 1 into 3 is plus 1. K is already given in the question, so I just took as it is equal to 10. K by 0 plus 1, 0 plus 1, 0 plus 1. So K equal to 10 is your first answer. The second question is the phase margin of the gain compensated system that we can do it in MATLAB. Okay, this question is based on MATLAB based. We did this so far. I will look for question that is formula based or to search solve by hands, like minimum marks question. Okay, this is my phase plot. Phase in degrees, magnitude in decibels. In magnitude plot, I want to start from 250 and digits from 250, 100, 50, 0, minus 15, minus 100. Still go till 150 also. Magnitude in decibels. Now, the phase magnitude starts between 200 to 150 and it keeps descending until it reaches around 0. So between 0 until this point, it comes just steady slope. It's a rough asymptotic plot only, but okay. After this, it has little bit slanting slope. It looks similar, but some slanting slope. Okay, with this information, with this knowledge of the bode plot, can you say what is the type of the system? Just guess what is the type of the system. Nothing else. No other information given. Just use this and use this magnet. So if this is 10 power 4, it is 10 power minus 2, and use this information, cutoff frequency and the magnitude descended, starting magnitude.
It's definitely not type 0.
Oh, good. How do you find the slope of the system? dy by dx.
Yes, ma'am.
If you find dy by dx, okay, I will give you one more information. At 10 power minus 4, this is around 150. It starts at 180, let's take. Roughly, I'm saying 180, 190. Just put that. Fine. Now fine.
And then it's type 2.
Type 2. Good. It's a 40 degree, 40 decibels per decade slope, right? So it
Yes, ma'am.
corresponds to type 2 system. So if you have a very detailed magnitude plot, if you ask questions like this, will you be able to find the transfer function types and whether from the transfer function whether the system is stable or not? These kind of questions you would expect that from that.
Yes, ma'am.
So when you see around this point, your magnitude is zero, right? So when the magnitude will be zero,
The screen is gone.
yeah, yeah, I'm doing it. When your magnitude will be zero,
Um,
like how we will be interested in magnitude zero. Phase margin occurs.
and steady state error.
Yeah. So we will call this as a gain crossover frequency where phase margin occurs.
Yes, ma'am.
So your gain crossover frequency within this will be around zero point 0.5. It's in between 10 power minus 1 to 10 power 0, that is 1, 0.121. So maybe around zero point 0.5 I'm taking approximately. So your omega GC would be equal to zero point 0.5 radians per second. This information we can get. Then phase crossover frequency, how you will calculate. It will be corresponds to minus. Okay, I didn't give the this one information, right? Okay, this is at 180 degree phase and
Yes, ma'am.
phase in degrees. Gain margin occurs at minus 180 degree, right? So here the phase is there at minus 180 degree for a longer period of time. So when it changes, mm,
This the same point for radius.
around point 1, yeah, around this point you will take point 5 radius. This will be around 0, 1, maybe around 1 frequency we can take.
Yes, ma'am.
Right. So I'm approximating it
So
here.
even if it is staying for 180 for a long time, we take the frequency as where it changes, is it?
Yeah. Uh,
Okay.
this is an approximate plot, right? So I'm just giving information from the image. So
Yes, ma'am.
let's take here around 1. So your phase crossover frequencies. In actual bode plot, you will have all this information. I just
Yes, ma'am.
drew it here, so it is like 1 radians per second. If for us, for now, we are taking it. This is phase crossover frequency. This gain crossover frequency. You're just investigating from the bode plot. Okay. So from the initial slope, we can say it's a type 2 system. So with that, we can ensure that two poles are there at the origin, right? The partial transfer function will look like this. So the type of the system, that's why the type of the system is two.
Yes, ma'am.
How do you say the system is stable or unstable without having the entire transfer function? There is no further slope change. You only know here there are some changes, but we don't know exactly from this rough plot. It's a handwritten plot. So, any idea you have whether to say whether the system is stable or not? Well, which side you can go with this origin? This is marginally stable, but if I want to comment more on the stability, just intuitively, anything you can get in mind, I will anyway going to tell, but just guess.
Only the poles can tell.
Only the poles can tell the stability. That's okay. Another way to find this is first you have to say see whether the gain margin is positive or negative.
Oh, yes, ma'am.
If the gain margin is positive, then you can say at gain crossover frequency or gain crossover frequency, the phase will be whether the phase is greater than or equal to minus 180 degree, like greater than or lesser than minus 180 degree. If the gain margin is positive and the phase is greater than minus 180 degree, then phase margin is also positive.
Yes, ma'am.
Here phase margin is positive. Okay, we don't know that. Just for the case, you know all the details I'm saying. When gain margin is positive and phase margin is positive, then the system will be stable. If something goes negative, then it will be unstable. From the bode plot also, we can say whether the system is stable or this is like 80% sure, kind of.
Oh, yes, ma'am.
Because bode plot itself it's an approximated plot, right? We cannot um, come to a conclusion fully, but if both the gain margin and phase margin is positive, then the system is stable. That's the maximum thing we can tell out of. Okay, that's it for this question. We solve this problem, no? 1 by s into s plus 1 before. So I will take similar problem that is s plus 2 now, and we just try to solve it by hand so that you know both by MATLAB and by hand how it is. The desired requirement is the KV should be equal to 10. So the first question is what is the gain value K similar to the problem we solved. How do we find it's a KV? Then it is limit s tends to 0 s into g of s. So it will be limit s tends to 0 s into k by s into s plus 2 equal to 10. S will get cancelled. K by s plus 2, k by 2 equal to 10, k equal to 20. So this is your k. So your gain adjusted system is, so in that problem k is equal to 10 because it is k by s plus 1, s into s plus 1. That's why this will be 20 by s into s plus 2. This is your gain adjusted system. Right. The second question is, this is first we found out. The second question is what is the phase margin of the gain adjusted system? To before finding the phase margin, we have to find the gain crossover frequency. How do you find? I am just going to take this as cap. Okay, just to identify it as a gain adjuster system, not the original system. How do you find the gain crossover frequency? We will find the magnitude of this gain adjuster system at the frequency where it is a gain crossover frequency. So omega should be omega GC when this will be equal to 1. At gain crossover frequency, your magnitude will be equal to 1. That's where you find. So we will just equate this to the magnitude law. So you will get all this j omega if I replace plus 2 equal to 1. I'm going to replace all the j omega with j omega gc because the omega is considered here into j omega gc. Omega gc plus 2. I'm going to take magnitude here after only, just rewriting this explanation. So you will get omega gc into root of omega gc square plus 4 in magnitude. So this will be omega gc into root of omega gc square plus 4 equal to 20. Omega gc square to omega gc square plus 4 equal to 400. Omega gc. How can we take this? Omega gc power 4 plus 4 omega gc square equal to 400. How usually we will find this?
We put omega GC square is equal to T, then T square plus 4T.
Oh, like this. So I will approximate this equal to x if I take x into x square plus 4 kind of. Sorry, x
Yes,
plus 4 equal to 400. X square plus 4x minus 400 equal to 0. So 7, 84, 6, right? Divided by 2 minus 2 plus or minus. How can I factorize this? Yes, square plus 4x plus 4s plus minus 400 equal to 0. Okay, it has given x is
no,
equal to
that's 16 plus 1600.
uh, plus or minus 1600.
Yes,
J
root,
will become
root. No, J and
okay, no J. It's a real values only.
16 plus 1600.
Okay, wait. Minus 2 plus or minus
Square root of 16 plus 1600. 1600
okay. This
by
is the
2.
4. Oh, okay. Okay, that's how you got it. Right, I can always do this. SQRT of 16 plus 1600. 40 around it is giving by 2
Yes, sir.
minus 1 plus or minus 20. It's around minus 19, comma, minus 20, 21, right? Plus 21, comma, 19 are those omega GC. Sorry, X, right? So now we have to find it omega GC. Okay. Um, so it's square root of this, right, for omega GC. because x is equal to omega gc square.
Yeah. Numerator it's minus 4 one instead of minus 2.
Ah, yeah. So this will be 2. Right? 18 it will be, or 22. Around this, okay? If it
18, 18.
comes, uh,
18.
it will come 18. So we will be omega gc is equal to root of 18 around it will, we will take. So this will be around 4.25. Similar to that, it will come. So this is your omega gc. If we find this omega gc, then if finding phase margin is easy. It's around 180 again plus your phase angle at g of j omega into gc of j omega if you have a compensator at omega equal to omega gc. So your transfer function, we know what is the transfer function 1 by s. If we find the angle for this, it will be minus 90 for 1 s and minus tan inverse of 2 by 1 for this transfer function poles. Then it will be minus 90 minus tan inverse of omega gc by 2 it is. Omega by 2 because 2 is your constant. Omega is your imaginary value j omega. Okay, this will be 90 minus tan inverse of omega gc is 4.25 by 2. Right, this will give me some 2 point something. Tan inverse, taking tan inverse for this, that will give me in degrees, it will be 90 minus 64 around. I'm getting in degrees. So your phase margin will be 36, 26, right? 26 degrees
Yes.
is your phase margin. What is the next question? What considering beta equal to 10? So it is a lag compensator. T equal to 10. What is the phase margin of the compensator system? So just substitute, first find the omega m, sorry, wm for that. WGC first we will find. Again to find the phase margin, we will find the omega gc. It will give me g of s into gc of s equal to 1. Again, we have to do all those things for both. It's a headache only. Plus 4 into what is GC? If beta equal to 10, 1 plus 10t divided by 1 plus 100, sorry, 1 plus 10 s divided by 1 plus 100 s it is. So it will be root of 1 plus 100 omega GC square divided by, oh my god, this is too much, 10,000 omega GC square is equal to 1. That's how tedious is it to calculate everything by hand.
Yes, ma'am.
So how can I don't find anything easy to do this.
Oh, this is for the compensated system, is it?
It's for the compensated system. Okay. Anyway, omega gc square, omega gc square plus 4. I have taken square, like square of this to get rid of the root. And I have taken square of this also, this term. That will give me 1 plus 10,000 omega gc square equal to this left hand side, numerator, denominator is in the left hand side, so numerator will be in the other side, right hand side. I'm going to write this will be 400 into 100 omega g square plus 1. They separated into numerator and denominator, that's it. So this will be We have to solve this. GC square 4 plus omega GC square into 1 plus 10,000 is equal to 400 into plus. Any way to cancel out anything to make it easy? Don't think so. We do this omega GC square into 4 plus 4,000 omega GC square plus omega GC square plus 10,000 omega GC power 4 equal to 400 plus 40,000. Oh, this is 4,000, this is 40,000. No way to cancel anything. Power 6 it is. No way we can solve this by hand.
Cubic equation.
Yeah. This will be omega GC6 plus 4,001. Minus 3,966. Oh, sorry, 96. Minus 400 equal to 0. Let me know if I missed something. Substituting x for omega GC square will be
It's 10,000.
10,000. Oh, I'm going to get help from the internet cubic equation solver. You can do that in calculator.
No, man.
We cannot do cubic equation in calculator. How anyone solve it using that? Minus 3996. Okay, this is the values they have given. Minus 8, 2, 0.093, 0.518. So out of this, we will take this positive value. So omega GC square is equal to 0.51 something. So omega GC will be 0.74. Around 0.71 radians per second it is flowing. So finding the new PM will be 180. This is to let you familiarize with all the equations, formulas at omega equal to omega GC. So this will give me 180 plus for the transfer function we already know 90 that is the open loop transfer function tan inverse of omega GC by 2. This is for our 10 by s into s plus 2. For the compensator, this is our compensator, right? Where it is This is the original gain adjuster system. It is the compensator I have. Ah, this is some. This is our compensator. So this will be again tan inverse of 100 omega GC plus tan inverse of or minus it will be. So this will be tan inverse of 10 omega GC minus tan inverse of 100 omega GC by 1 more that we don't want to convert. So if I solve 180 minus 90 minus omega GC is everything everywhere omega GC should be 0.7. 0.7 by 2 0.35 something 356 something by 2 sorry by 2 won't come right plus tan inverse of 7 minus tan inverse of 70.71 is 7.1. This is 70.1. Okay, nice. 71. Just right. Doing all this math. I am getting around 60 phase margin. This is the phase margin of the compensated system.
Okay.
And last question. Frequency at which the maximum phase lead occurs. We use that dip to find the in the bode plot, right? Now we can use this formula straight away 1 by 2 beta into t. Beta they have given 10, t is also 10. So it will be 10 root 10. How much it is? Root 10 it is. I think can be separated. Root 5 into root 2, 1.5. Better I will separate. 0.03. Okay, that's it. So yeah, I hope we have familiar with all the body based design, root locus based design. I can submit the assignments. If you have any doubts, you can ask me during Monday class. Thank you.
Okay, ma'am. Yeah, thank you, ma'am.